So greetings. Welcome to today's class. So let's quickly recall what we were doing. So we were looking at cornering dynamics, and in yesterday's class we started off with the kinematic bicycle model. And if we recall, by the bicycle model, we are going to refer to an approximation where we combine the two front wheels as one and the two rear wheels as one. Okay? So a four-wheel vehicle is visualized as a two-wheel vehicle. And the kinematic bicycle model, we are going to neglect the so-called slip angle. So we will look at what is called as a slip angle later on. However, the bottom line is that we are essentially going to deal with only the motion of the vehicle. We are not going to consider the forces and torques that create the motion, right? So we are dealing with kinematics in general, right? So that's what we are going to do here. And so we essentially constructed this diagram, and without loss of generality, we assume that both the front wheels and the rear wheels are steered by angles delta F and delta R respectively. And we constructed this diagram, and we identified a measure called beta, which is the side slip angle. So as we discussed, this should not be confused with slip angle. The side slip angle essentially indicates the angle which is made by the velocity vector, which is perpendicular to the line segment OC, right? And the longitudinal axis of the vehicle, which is represented by AB. Okay, so that's what the side slip angle is. So what we want from the kinematic bicycle model is a model that provides relationships between the time evolution of this important parameters X, Y, and Psi, which characterize the motion of the vehicle with time. Then the inputs given to the model are going to be the steering angle, okay, in addition to information on the vehicle speed and so on. Okay. So now, in fact, if we look at the capital X, capital Y axis, which is the global frame of reference, we can immediately write down the evolution equation, and then we are going to simplify and get the final equations of motion as far as the kinematic. So if we recall, our vehicle is indicated by this line segment AB, okay, as far as this visualization is concerned, and let's say the center of gravity of the vehicle is at point C, okay. So as we already know, let's say the velocity vector at the center of gravity, let's say it is in this direction. This angle is going to be beta, okay? Obviously, beta is going to be a function of time. And the angle which longitudinal axis of the vehicle, makes with the capital X axis or the global X axis is the heading angle psi, okay? So that's what we have. So totally the sum of these two angles, so the angle made by the vector, the velocity vector V with the global x-axis is going to be psi plus V. I'm sure all of us can immediately identify this, right? So to begin with, the governing equations of the kinematic bicycle model. If we recall, as far as our notation is concerned, when we put a tilde underneath a character, we are talking about the velocity vector, right? So this is the velocity vector at the center of gravity, right? So please remember that. Okay, so we are essentially going to resolve it along the capital X and capital Y axis, and then get equations of motion. Okay, so that's what we are going to have. So the governing equations of the kinematic bicycle model can be written as the following. Okay, so bicycle model can be written as, okay, so first if we resolve the velocity vector along the capital X axis, we are going to get the X component of the velocity vector, which is nothing but X dot, right, which is dx dt. And what is that component? Is the magnitude of the velocity vectors V multiplied by cos of the angle, right? What is the angle made by the velocity vector with the global x-axis? It is psi plus beta, right? So now I'm going to write psi as a function of time and beta as a function of time. Okay, so that like it's clear to us what we are dealing with, right? So we are essentially we want to clearly indicate which variables are functions of time and which variables are constant. Of course, we are going to assume that the velocity vector is constant, right, in magnitude. So we are essentially going to deal with the case where the vehicle is traveling at a constant velocity. Okay, so that's an assumption that we are going to make. Okay, so given that this is going to be x dot equals d cos psi of t plus b of t, and y dot of t is going to be v sine of this angle. Okay, we are essentially resolving it along the global x and global y axis, right? So that's what we are. And what is xy? Xy is the coordinate of this point C, right? So x comma y denotes the coordinates of this point. Okay, and essentially we are going to get psi dot, okay, which is going to be what is called as a yaw rate. It is going to be v by r. Okay, so we assume that like we are going to have the object or the car rotating about the instantaneous center of turn, like in with a constant speed. So the yaw rate is nothing but v by r. Okay, so we get this from rigid body mechanics, right? If you have a particle which is rotating at an angular speed omega, the tangential component v is going to be r omega, right? So that's what we are. So the psi dot is nothing but omega. Okay, so these are the three equations, that essentially provide the governing equations as far as the kinematic bicycle model is concerned. So we can see that we have an evolution equation for psi x, y, and psi. Okay, so please remember psi dot is what is called as the yaw rate. Okay, so this is the time rate of change of the yaw angle. Okay, and what do we mean by evolution equation? So you can observe that like we are getting an ordinary differential equation in time, right? So these equations show us how the parameters are varying with respect, or the variables are varying with respect to time. Okay, so of course, if I have to solve these equations, like I don't know beta and r, right? So we need to find, right, beta of t and the turning radius r, right? So we don't have that value because see, we know what is the speed of the vehicle. We know delta f and delta r. Okay, so we need to find out beta and r so that like I can solve this model and do something meaningful, right? So just for the sake of convenience, let us suppress the symbol function of time from here onwards. Okay, so just for notational convenience, like it should be very obvious to us from the usage as to which variables are functions of time and which variables are going to be constants. All right, so let's do some simple geometric analysis to simplify these. So going back to the diagram that we have, we are going to use what to say, essentially simple geometry to get beta and r. So first, we can observe that there are. Yeah, please go ahead.
Usually, when the front wheels are steered, does the rear wheels also slightly steer a bit?
I'm sorry. Can you repeat the question? Your voice I could not hear clearly. Please.
Is it better now?
Yeah, please go ahead. Let me see.
While the front wheels are actually steered in the vehicle, does the rear wheel also slightly change the angle during the turn?
I am sorry, I did not get the question. When the front wheels are steered? No.
When the front wheels are steered, does the rear wheels also slightly steer a bit to complement the front wheel steer?
Okay. So we will go to the dynamic bicycle model where we will learn about rear wheel slip. Okay, so there we will observe that we will only consider the case of front wheel steering and the rear wheel will slip. Okay, as a consequence. Okay, so this kinematic model is only an approximation. Here you can put delta R to be 0 also. Okay, yeah, absolutely no problem. We are only considering the generic case. But if you look at most vehicles, like the rear wheels are non-steerable, right? So what may happen is that like there may be some deformation in the rear wheel assembly, corresponding to the cornering motion. Okay, and there may be changes in the alignment of the rear wheels with respect to the vehicle body and also the axle. Okay, so that can happen, okay, due to the various forces that are generated. But the conventional steering, right, as we know it, where we are essentially going to rotate the wheel about a steering axis, will not happen if we don't have rear wheel steering. Okay, yeah. So there may be other effects such as what are called roll steer effects, which can happen. Okay, so where the orientation of the rear wheels may change due to dynamics such as roll. Okay, but then here we are not going to consider it at this moment. Okay. Is that fine? No. Any further questions?
Yes, sir. Sir, I didn't understand this psi dot.
I'm sorry, can you repeat the question? I think maybe my internet connection is poor today. Sorry about that. Can you repeat the question?
Sir, you have written psi dot T is equal to V by R, right?
Yes,
So,
yes.
as I understand, this is we derived from V is equal to R omega, and omega is the angular velocity of that component.
Hmm.
So then, how does psi T is related to the change in the angular velocity?
So psi is the angle. Okay, psi is the angular displacement. Psi dot is omega. Right. So that is the first derivative of the angle, right? Is it? Okay. Yeah. See, psi, if you look at psi itself, right? Psi of t is nothing but the yaw angle, okay, or the orientation angle. Okay. As you can see, as the vehicle is taking a turn, you will be doing this as the next homework. I'll define the problem today. You will do a simulation and observe that this line segment AB will be changing its orientation with respect to capital X axis, okay, as the vehicle keeps on rotating. All right. So psi will keep on varying with time, right? But however, in the steady state model that we are doing, psi dot will be a constant, which will be V by R, okay, because there is no slip. What happens when there is slip? We will derive it and when we go to the dynamic bicycle. Okay, this is a simpler case. Okay.
Sir, omega is defined as d theta by dt, right? So
yeah, d theta by dt. Theta I'm calling as psi.
okay.
See, theta is any an angle measure, right? So it's convention to represent the yaw angle with the symbol psi. You can use theta also if that will be comfortable. But typically, theta, phi are all used for other angles. Like typically the symbol psi is used for the yaw angle. Okay. See, just like we have, x, y, z. Okay, we use theta, phi, psi. Okay. Theta is typically used for the roll angle, phi for the pitch angle, psi for the yaw angle. Okay.
Yes, sir. Thanks.
All right. So that it is just a convention, but it's an angular angle measure, right? So that's important. Okay. I hope that clarifies this question. Any other questions?
Sir, in the kinematic model above, if we make delta R 0, how will it affect, sir?
We are going to essentially derive the expressions, and as I told you, you will observe it in the homework. Okay, the homework problem which I'm going to give you, delta R will be 0. I am only deriving it for a generic case. That's all I'm doing. Okay, so please bear with me for maybe another 10-15 minutes. We will derive the expressions and then you will observe how delta R affects it and what will happen if delta R becomes 0. You will essentially do the simulation in your homework problem. That's coming. Shall we proceed? So now let's go back to the diagram that we were considering. So we saw that there are two triangles, right? OAC and OBC. So we are going to consider both the triangles, and we are going to use what is called as a sine rule. I am sure all of us would have studied about the sine rule in high school geometry, right? That's all we are going to use. So the sine rule says that sine of, if you consider a triangle, the sine of the angle divided by the length of the opposite side, that ratio will be equal. Okay, so you'll have three ratios, right? So we are going to apply it to both triangle OAC and OBC. So for example, if we consider triangle OAC, let's say we consider this delta f minus beta. Okay, so sine delta f minus beta divided by LF, because LF is going to be the opposite side, right? Is it not? Okay, that's going to be equal to sine pi by 2 minus delta f divided by r. Okay, so that is one relationship we are going to write down. Of course, currently we are not worried about the third ratio. That's why we are going to use only the two ratios. Okay, so I hope that's clear. So let me write this thing down. So consider triangle OAC. Okay, if we consider triangle OAC, what's going to happen is the following, right? As we discussed, sine of delta f minus beta, as I told you, I'm suppressing time, okay, within parenthesis time, okay? So it's understood that delta f beta are all functions of time, whereas LF is a constant, okay? That's going to be equal to sine of pi by 2 minus delta f divided by r. Okay, so this is something which is quite straight. And what is sine of 90 minus theta? It is essentially cos theta, right? So this is going to be cos delta, right? So this is also something which we know, all right? So now we go and expand this formula, okay? So this implies that what is sine of A minus B? It is sine A cos B minus cos A sine B, right? So we are going to expand sine of delta F minus beta as sine delta F cos beta minus cos delta F sine beta. So I'm not doing anything other than using basic geometry, okay? And we take LF to the other side. So I'm going to have LF divided by R cos of delta F. Okay, so this is what we are going to have. Okay, so if we divide both sides by delta F, what we are going to have is that, like, we are going to have tan of delta F cos beta minus sine beta is going to be equal to LF divided by R. Okay, so this is one equation. Okay, so I hope it's clear how we got this, right? Very, very straightforward. We are essentially using the sine rule from geometry and then like using the expression for sine of A minus B to get this simplified expression. Let's call this equation number one. Okay, so I'm going to call this set of equation as a block as using Roman numeral 1. Okay, this expression that we just derived, tan of delta f cos beta minus sine beta equals LF by R as equation number 1. Okay, so that's what we are doing. So this is what we get when we consider triangle OAC. Okay, so now let's go back and look at the other triangle. Okay, so if we consider now the triangle OBC and then like use the same sine rule, we will have sine of beta minus delta R divided by LR. Okay, that's going to be equal to sine of pi by 2 plus delta R divided by capital R. Okay, so that's what we are going to have. Right, I hope it's clear, right? So how we are going to write down this expression. Once again, we are using the sign. So let's go and write that one down. So essentially, let's consider triangle OBC. Okay, if we consider triangle OBC, we are going to have sine of beta minus delta R divided by LR. That is going to be equal to sine of pi by 2 plus delta r divided by capital R. Okay, so that's what we have. Okay, so this will essentially give, so from here, like we can once again see that sine of pi by 2 plus theta is going to be cos theta, right? So this is going to be cos of delta R. Okay, so we simplify this. Once again, we write the expansion for sine of A minus B. So sine of beta minus delta R is going to be equal to sine beta cos delta R minus cos beta sine delta R. That's going to be equal to LR divided by capital R cos delta R. Okay. Then once again, we divide both sides by cos delta R. If we do this, we are going to get sine beta minus cos beta and delta R, okay, is going to be equal to L subscript R divided by R. Okay, so it's pretty straightforward, right? So let's call this as equation number 2. So we essentially got this equation by writing down the sine rule for this triangle OBC and then like simplifying. Okay, so let's call this as some equation number 2. So we have got this, got these two equations, right? 1 and 2. So now what we are going to do is that like we are going to simplify these two. So first let's do 1 plus 2. Okay, we add equations 1 and 2. What do we get? We are going to get tan delta f. So pretty straightforward. Tan delta cos beta. Sin beta is going to cancel off, right? Because you can observe that there is one minus sin beta here and there is a plus sin beta here, right? So they will get cancelled off, right, on the left hand side. So what we are going to left is we are going to left with tan delta f cos beta minus cos beta tan delta r is going to be equal to LF plus LR divided by capital R. And what is LF plus LR? It is the wheelbase capital L. Okay, so this can be rewritten as capital L by R. Okay, so that's what we have. And this essentially will give us the following, right? So I can pull cos beta common on the left hand side. I'll get cos beta times tan delta minus tan delta. That's going to be capital L by R. Okay, so that's what we have. Okay, so consequently, we can get an expression for the turning radius R. So the turning radius R is going to be L divided by cos beta times tan delta F minus tan delta R. Okay, so this is the expression for the turning radius. Okay, so we have essentially used two equations that we have derived, right? So to get an expression for the turning radius R. However, you can immediately see that this turning radius depends on delta F and delta R. So now if delta R is 0, tan delta R will become 0, right? So we will only get tan delta F in the denominator, right? So I hope that is clear. However, if I were to calculate beta, I still need, if I want to calculate R, I still need beta, right? We are not done yet, right? So how do I get beta? So we are going to simplify a little bit. So what we do is that like we will take equation number 1 and then we will multiply by LR. We will take equation number 2, we will multiply by LF and then we will simplify. Okay, so let's see what comes out. Okay, so let's do that. Okay, so we have got an expression for R. So now what we do is that like we take equation number 1 and multiply by L subscript. Okay, so if I do that, what am I going to get? I'll get LR tan delta F cos beta minus LR sin beta is equal to LF LR divided by capital R. Okay, so what did we do? We just took equation number 1 and then multiplied both sides by LR. That's all we did. All right. So now we are going to essentially multiply equation 2, right, with LF. So what do we get? We take equation number 2 and multiply both sides with, we will be getting LF sine beta minus LF beta tan delta R is going to be equal to LR LF divided by, okay. So we take these two equations and subtract, okay, from each other. So what do we get? If we subtract, on the left hand side, we will see that we will have one term which will have cos beta common. Okay, the first term on the left hand side of the first equation, the second term in the left hand side of the second equation, right? So they will have cos beta common. So I will have cos beta times LR tan delta F plus LF tan delta. How did I get plus sign? Please note that you need to subtract them, okay, not add them. All right, and then I'll have LR plus LF sine beta, okay, because I'll have minus LR sine beta minus LF sine beta. I take minus sine beta common, I will get LF plus LR. And that's going to be equal to 0 because the right hand side are the same, right? Right hand side is the same in both equations, so they will cancel out, right? And as we know, LF plus LR is anyway capital L, right? So using this, we can immediately write that cos beta times LR tan delta F plus LF tan delta R, okay, is going to be equal to L times sin beta. Okay, so this will give us one equation for beta. So beta, if we divide, cross multiply, cos sin by cos is tan. Okay, tan beta will now become LR tan delta plus LF tan delta R divided by capital. Okay, so we have derived an equation for beta. Okay, so let's call this as equation number 4. Right? So this equation, we can immediately see that this is a solution for beta, and we can observe that this equation, right hand side of the equation, contains all known parameters, right? Delta F is known, delta R is known. Those are the inputs to the model. LF, LR, and capital L are known, right? So we can immediately get beta. Once we get beta at every instant of time, we can get essentially substitute and get R, which is the radius of the turn. And then once we get beta and R, we can go back and solve equation number 1, right? Roman numeral 1, okay? So if I were to simulate this kinematic bicycle model, we solve the set Roman numeral 1 along with equations 3 and 4. Okay, solve them numerically. Okay, to essentially simulate the kinematic bicycle model. So, in fact, if we look at the kinematic bicycle model using our system theory perspective, right? So, we were dealing with dynamic systems where we considered a system to be a block with inputs and outputs, right? So, if you look at a kinematic bicycle model from that perspective, so the kinematic bicycle model takes in the steering angle as the input, right? So of course it also uses the vehicle speed, but then like it uses the steering angle inputs delta F and delta R. And once again, if we see that if we don't have rear wheel steering, we just need to substitute delta R to be 0, right? So you can immediately see that in equations 3 and 4, delta tan delta R will vanish, right? Because delta R is 0 means tan delta R will be 0. Okay, so that's all will happen, right? So for the kinematic bicycle model, so the inputs will be delta F and delta R if applicable. Okay, so if delta R is 0, so we don't need it can be substituted as 0 and things will simplify. And then like what will be the outputs? So we have the positions X, Y, and psi. sorry, xy essentially denote the coordinates of the center of gravity with respect to the global frame of reference. Psi denotes the orientation of the vehicle with respect to the global axis, x-axis. Okay, so those are the outputs from the model. Okay, so I hope this is clear, right? Okay. So any questions on the derivation of the kinematic bicycle model? Okay, so if not, I'm going to essentially give you a homework problem to solve based on this. Okay, so what is this homework problem? So this will be a simulation exercise. So let us say we consider a vehicle which is traveling at, let's say, 4 meters per second, right? Whose wheelbase is 3 meters, and the center of gravity position is such that LF is 1 meter, and it is given a front wheel steering angle input of 8 degrees, and there is no rear wheel steering. Okay, delta R is 0. Okay, so let x0 be 0, that is the initial condition, be all 0. Okay, so I will explain what this means physically shortly. So let's say x0 is 0 and y0 is 0, psi 0 is 0. Okay, so consider, let's say, time interval t between, let's say, 0 to, for example, 30 seconds. All right. So I want you to solve the model for this time interval. So please solve the kinematic bicycle model using a simulation tool. For example, if you have MATLAB, you can use that. Nowadays, MATLAB online version is there, and as anyway, you will be having access to MATLAB through your IITM account, right? So you can always solve that. If you want an open source software, there is an equivalent software called Scilab, which you can use, and then you can do the simulation. So please do the simulation using the tool which is convenient to you. So simulate the kinematic bicycle model and plot the trace of the vehicle. Okay, so essentially you need to plot the trace of the vehicle. So what do I mean by the trace of the vehicle? So let me explain what I'm expecting, right? So let us say once again we have the global Excel, right? Okay. Now let's say this is the origin. Now at time t equal to 0, what's going to happen is the following, right? The vehicle is going to be here. Okay. So this is the vehicle AB. Okay, the point C, which is the center of gravity, which is going to be at the origin, right, at time t equals 0. So this is what is meant by the initial conditions being 0, right? So the coordinates of the CG are at 0, 0, and also the yaw angle of the vehicle is also 0. Okay, so this is the one. Of course, LF is 1 meter. That means that LR is 2 meter, right? So the CG is closer to the front than the rear, right? So that's why I have drawn the line segment like that. Okay. So please note that LR is going to be capital L minus LF, right? So LR is going to be equal to capital L minus LF, which is going to be 2 meters. 3 minus 1 is going to be 2. Okay. So that's something which we can obviously realize. Now, if you simulate this, you will get a time profile where the vehicle will essentially start turning. Okay, and this profile will go something like this. Okay, so the yaw angle will become non-zero, the coordinate will go away from 0, and then slow. Then I'm just drawing some. You can get the exact curves. Okay, when you essentially simulate, but then you will see that the points A, B, C will trace a curve, and then the yaw angle will also be changing with time, right? So I want you to generate this trace. Okay, and then please submit a single PDF file with the code, the plots, and the discussion. Okay, so that is what I want you to do as homework number 5. Okay, so I will enable a link. Okay, so submit a consolidated PDF solution 5. And I will create a Google form and share it in the Google Classroom, and then you can upload it using that Google form. And it's solution 5, which contains the code corresponding simulation plots and discussion. Okay, your comments also. Okay, so please submit as a consolidated file. Okay, so this is your homework number 5. So is it clear what is the problem statement and what I expect you to do? Any questions on homework number 5?
Sir, the velocity will start increasing from 0, and then by the end of 30 seconds, it will reach 4 meters per second. Is it?
No. Velocity, you can take it to be a constant. Okay. So at time t equals 0, it is at the origin. Okay. Yeah. It will start moving at 4 from time t equals 0 itself. Okay. So that's the simulation here. So this is not an acceleration maneuver. This is only a cornering maneuver. See, imagine that the vehicle was traveling along the capital x-axis at 4 meters per second, okay, before the steering wheel is turned, right? Now, let's say we call the instant at which we do the steering as time t equals 0, at which I am giving a steering angle of 8 degrees. So what happens to the path trace of the vehicle? Okay, so that's what we are trying to evaluate. Is it clear?
Yes, sir.
So the vehicle is not stationary. It's already moving at a uniform speed of 4 meters per second at the beginning of the cornering. That's a good question. Okay, so the vehicle speed is always 4 meters per second throughout the maneuver. All right. Yeah. Any other questions?
Sir, we'll have to plot the trace for what times are actually from 0 to 30 for what times.
For what time? Okay, you can decide. Okay, maybe you can do the simulation for, let's say, every 1 millisecond or 10 milliseconds and so on. But if the trace becomes very dense, you can plot the trace for every half a second, right? But do the simulation for a finer time interval. Okay.
Okay, sir. Okay.
Yeah. So I'm sure we can figure those things out. So please do try. If you have any queries, let me know. Okay. So yeah. So once again, this is going to be a simulation exercise, right? So so you have to do the coding part. Okay. So this you need to submit as a homework.
So we can use Octave.
Absolutely. Yeah. You can use Octave. You can use what is called Scilab. Okay. You could use whichever software that you are comfortable with. I have no what to say restriction in that regard. Okay.
Okay, sir.
Yeah.
Sir, in the like above, you drew this model and like inputs and outputs. I'm confused. Like how beta is not a part of that model.
Beta is sort of like an intermediate variable. See, beta is coming in the model equation. We can have beta as an output, but then like we are going to visualize this kinematic bicycle model as one, which currently gives us the position and the yaw angle. Okay. If beta is of interest, we can view that as an output also. Absolutely no problem. Okay.
Okay.
Yeah. But then like as you would have realized, in order to get psi, we needed that psi and x and y, we needed beta and r, right? That's why we solved for them. Okay, great. So yeah, any other questions? Okay. So if not, let me introduce the concept of the slip angle in the remaining time, and that will take us to the discussion on the dynamic bicycle. Okay. So in reality, like when essentially a pneumatic tire is turned, right? So what's going to happen is that like we have a rolling tire, right? Which is essentially rolling and moving forward. And suddenly we steer it. So the orientation of the tire plane is changed, right? And we essentially have a rolling tire. And when a point on the tire comes in contact with the ground, like it is going to stick to the ground, okay, and there is going to be some friction available at the tire road interface. Consequently, the tire sidewall is going to deform, okay, during the turn, and that is going to create a slip angle and a consequent lateral force, or a force along the lateral direction, which will help us in taking the turn. So what do I mean by that? Okay, so let me draw a simple schematic and explain these ideas. Okay, so when we are essentially dealing with a zero slip angle, okay, which is an approximation, okay, which is okay at low speeds, and we are considering the kinematic model. Let us say, like we have a tire that has been turned. Okay, so let's say this is the top view of a tire. Okay, and it has been turned. This is the central wheel plane of the tire. Okay, and let's say this was the original. Sorry about that. Like 1 minute. Let me draw in a different color so that it's clear to us. So let's say this was the original direction. Okay, and then like we take a turn. So what's going to happen is that, like, let's say when we don't have any slip angle, the velocity vector, right, is going to be oriented along the plane, the direction of the central wheel plane of the tire. Okay, so this is going to be the case of zero slip angle. Okay, but in reality, what's going to happen is the following. Okay, so let's now discuss the notion of the slip angle. So let us say, once again, we have a tire. I'm just going to draw a bigger diagram just to convey the concept. This is an exaggerated diagram. So just to convey the concept to us. So what will happen is that, like, let's say I turn the wheel tire assembly like this. Okay, so this is my initial position orientation, and then like we turn like this. Okay, so my central wheel plane is something like this. Okay, red line indicates the central wheel plane. So now what will happen is the following. Okay, so the velocity vector due to the slip which takes place in the lateral direction, right, due to the friction available at the tire road interface and the deformation of the tire, okay, the velocity vector at the tire road interface will now no longer be along the direction of the central wheel plane. Okay, it is going to be in a different direction. Okay, and the angle which is made by the velocity vector with the central wheel plane is what is called as a slip angle. Okay, denoted by the symbol alpha. And if you look at the forces at the tire road interface, there are going to be two components. One component, which is going to be along the x-axis, which is going to be along the central wheel plane, is the longitudinal force Fx. And we are going to have a force which is going to be perpendicular to Fx, which is along the local y-axis, which is called as the lateral force. So Fx is the longitudinal force. We will revisit the longitudinal force when we look at longitudinal dynamics, okay, where we consider both drive and braking. So this is the longitudinal traction, longitudinal force at the tire road interface, and Fy indicates the lateral force, okay, the tire road interface. Right? Now, this lateral force depends on the slip angle. Okay, so it has a relationship to the slip angle. It is also related to other quantities. Okay, the relationship between the lateral force and the slip angle also depends on the normal load. It also depends on what is happening along the longitudinal direction, which we will learn later, like we'll introduce a parameter called longitudinal slip ratio or the wheel slip ratio. Okay, so this curve is going to depend on this relationship is going to depend on those variables too. But then, like right now, we will consider what is called as the pure slip model. Okay, so we are only going to consider lateral slip. Okay, so the relationship between the lateral force versus slip angle is going to be something like this. In the initial part, okay, so it is going to be almost linear, and then it will reach a peak, and then like it will start decreasing. Okay, so this is how it will look like. And in the initial part, like this is going to be almost a linear curve. Okay, and this is what is called as a linear region, okay, of this Fy alpha curve. All right, this is what is called as the linear region of the lateral force versus slip angle curve. Okay, so this Fy alpha curve becomes very important for modeling cornering dynamics. Okay, as I mentioned, we are considering what is called as a pure slip model or a pure slip condition, wherein we are essentially considering only the forces along the lateral direction and slip along the lateral direction. Of course, when we consider drive and braking, we will be considering slip along the longitudinal direction through what is called as a wheel slip ratio or the longitudinal slip ratio. In real life, we may need to deal with what is called combined slip. See, imagine that we are turning a vehicle or a car and we may brake. So then there will be slip along both the directions. So combined slip becomes a little bit complex. So we will visit them later, right? So right now we are going to consider what are called pure slip conditions, okay? And considering pure lateral slip and linear region of operations at small slip angles, okay, within quotes of a few degrees, right? We can observe that the lateral force which is generated at the tire rod interface is proportional to alpha, okay? And this implies that the lateral force can be written as some constant C alpha times alpha, okay? So this C alpha is the constant of proportionality, okay? So this C alpha is what is called as the tire cornering stiffness, okay, and is a very important property as far as the cornering dynamics is concerned. Okay, so we will derive the dynamic bicycle model starting from the next class. We will observe how C alpha comes into the picture in the governing equations, and then using this, like we will do a stability analysis of cornering dynamics that will use a parameter called as understeer gradient, and we will learn what is meant by understeer, neutral steer, and oversteer conditions, what is called as critical speed, and then like when will a vehicle potentially become unstable during a cornering maneuver and so on. Okay, so those are all discussions that are going to happen in the next few classes. Okay, so I think this is a good place for me to stop here. So we have looked at the kinematic bicycle model. We will look at the dynamic bicycle model in the next class. As a precursor, I just introduced this notion of slip angle and how the lateral force at the tire rod interface depends on the slip angle. And we are going to consider a linear model for the tire lateral force in our derivation, wherein we are essentially going to take the lateral force Fi to be some C alpha times alpha. Okay, C times C subscript alpha, just to denote that we are dealing with the cornering stiffness. Okay, so C alpha represents the cornering stiffness of the tire. All right. So, if are there any questions about what we have discussed in today's class? Okay. So if not, let me stop the recording.